Ever wondered what the universe is really made of? At CERN, physicists smash particles together to unlock answers so bizarre they'd make even Einstein raise an eyebrow. This is unbelievably science. And we're unraveling the newest subatomic surprises shaking up the standard model. Think mystery particles, fleeting forces, and cosmic clues hiding in plain sight. Buckle up, particle physics just got stranger than fiction. In the darkened depths beneath the Franco-Swiss border, a machine stretches for almost 17 miles. A ring of such ambition that it can recreate moments mere fractions of a second after the birth of our universe. This is the Large Hadron Collider, or LHC, CERN's crown jewel, and the site where reality's most elusive building blocks are hunted with exquisite precision. Picture protons hurtling toward each other at nearly the speed of light, 99.999999. 1% that of a photon. Each collision is an alchemical experiment, a controlled explosion so intense it births particles never before seen in the history of Earth, if only for an instant. The detectors, ATLAS, CMS, LHCb, ALICE, stand by to capture these ephemeral traces, like high-tech nets catching stardust in a hurricane. Not all discoveries at CERN are planned. In 2015, scientists stumbled upon something wholly unexpected, the pentaquark. A particle comprised not of 3 quarks like protons and neutrons, nor 2 like mesons, but 5. A combination theorized since the 1960s yet elusive until now. It was like finally finding a new species in a forest you've walked your whole life. Let's dive deeper into the pentaquark mystery. To physicists, quarks are like letters in an alphabet. Combine them in different ways and you build everything from protons to exotic particles. But nature's rules for assembling quarks are strict and quirky. Most combinations fall apart instantly. The pentaquark's stability surprised even seasoned experts, hinting at unknown forces binding quarks together in ways textbooks couldn't predict. The hunt for new particles at CERN isn't just about finding stuff. Every new discovery is a stress test for the standard model, the seemingly unbreakable blueprint that has governed particle physics for half a century. But new arrivals like tetraquarks and pentaquarks suggest cracks in this venerable theory, opening tiny windows through which deeper truths might be glimpsed. Imagine standing inside one of CERN's gigantic detector caverns. Towering walls glitter with electronics, thousands of cables, snake-like arteries across the floor, and every second, raw data streams in equal to millions of HD movies. Only by sifting through these mountains do scientists spot patterns, rare anomalies that could herald a new particle, or perhaps rewrite our understanding of matter itself. One electrifying moment came with the tantalizing bump observed in 2016. A possible new boson weighing around 750 gigaelectronvolts. Though it disappeared with further data, it galvanized physicists worldwide with speculation. Were there hidden dimensions? New forces? Sometimes what we don't find shapes our theories as much as what we do. Certain experiments seek more than just particles. They seek answers to cosmic riddles. Why is our universe dominated by matter rather than antimatter? The LHCb experiment has uncovered subtle differences in how certain particles called B-mesons decay versus their antimatter twins. These minor violations hint at mechanisms that could explain why anything exists at all. For many, particle conjures something tangible, a minuscule grain or speck. Yet many newly discovered particles are resonances, fleeting blips that survive only trillionths of a second before vanishing. What we learn from their decay patterns offers profound glimpses into forces that shaped the infant universe. Defying expectations yet again, in recent years CERN found evidence for tetraquarks made entirely of charm quarks, the heaviest such grouping ever seen. Theory suggested they shouldn't form, nature proved otherwise. These findings prompt deep questions about how strong forces glue matter together, and whether even stranger quantum molecules await discovery. Some discoveries challenge our deepest assumptions about symmetry and balance in nature. Take lepton universality, a principle suggesting that electrons, muons, and tau particles should behave identically except for their masses. Yet anomalies detected by LHCb suggest otherwise. Muons aren't following the rules. Is this an early sign of new fundamental forces weaving unseen through reality? The legacy of CERN is not just cataloging exotic matter. It's about teaching us humility before nature's complexity. Each time physicists think the zoo is complete, a proton here, a neutron there, nature unveils another enigmatic beast. Hidden just out of view, beauty quarks pairing up in unprecedented ways, charm decaying with whispers of physics still unimagined. Beneath all this lies a kind of poetic detective story. From analyzing how jets of subatomic debris curve under powerful magnets to reconstructing the family trees of decaying particles, every step brings us closer to answering primordial questions. Why does matter have mass? Do hidden symmetries shape reality's fabric? Think about this. When scientists smash protons together at colossal energies, they're probing not just matter's structure but what lies beyond it, clues to dark matter candidates like sparticles, theoretical supersymmetric partners still lurking undetected but driving innovation and hope on every data run. If you enjoyed these unbelievable facts, don't forget to like and subscribe for more mind-blowing science every week.